Okay, so the next thing that we're going to discuss are budgets. So we hinted at what a budget is, both in class and in some of the last lectures. So I'm going to pick up now and we're going to get a little bit more quantitative about what we mean. Okay, so the first thing we want to keep in mind is what the difference between Eulerian and Lagrangian are. And here's a simple example. This little movie shows a wave-like feature that is propagating to the right. It's being advected to the right by a velocity u. And so a Lagrangian perspective would follow the fluid parcels. So it might move along with this crest of the wave or move along with this trough of the wave. And in that perspective, your position is changing, but not the magnitude of that piece of fluid. By contrast, the Eulerian perspective sits still and watches the flow go by. So here is an Eulerian perspective, this little black dot that's going up and down. You notice that it's not moving, it's going up and down to detect the changing signal in time, but it is staying fixed, at least in this direction, in space. And so the Eulerian perspective is focused on the rate of change and the things that are flowing in and flowing out. The Lagrangian perspective is based on the total derivative, including the motion of the parcel following the fluid. So why don't we do everything in Lagrangian fluid mechanics? I mean, Lagrangian is the sense that you probably took intro to physics classes with cannonballs and ball bearings and masses on springs and all that kind of stuff, or you might have thought about it from the perspective of driving in a car or playing a sport. Why we don't use that for fluid mechanics very often is because the fluid is a continuum. It has fluid at many points in space. So exactly how many water parcels would you need, a parcel being a small hunk of water, to consider the motion of a turbulent fluid? You need a parcel at least for every kind of coherent moving part of that fluid, which would be a very large number of parcels. Also, you have to wonder, when the parcels are moving along, how do you interact them with the boundaries? They're going to be moving by, and so a parcel doesn't stay a boundary parcel. It might move into the interior and be replaced by another parcel as it's getting stirred up. And we know from celestial mechanics that as soon as we get to 3 interacting bodies, we tend to be in trouble in terms of being able to solve those equations accurately. There are some interesting exceptions to this rule. There's one paper by Hartel and Randall, and there's another where they imagine that they can model the ocean with slippery sacks that slide over each other. There's another fluid dynamics numeric scheme called smooth particle hydrodynamics, which is sometimes used for planetary sciences. Okay, so we have an Eulerian perspective, we have a Lagrangian perspective. We could think of a tiny parcel that's just a point, essentially. But that parcel could have a budget, but actually when we normally think about budgets, we're thinking about a finite volume of stuff. So we might have what's called a control volume, which is an Eulerian concept. This is just could be a rectangle, it could be another shape, but it's something that's held fixed in time as the fluid goes by. And so here, this is the conception that we did in the homework. Here is, say, an x, and then here's a displacement x plus delta x to and a little bit larger value of x. Inflows of velocity with u into the face, which is, if this is the y direction, delta y is the length in that direction, delta z is the length in that direction. So let's do the units. We have a density, velocity, length in y, length in z. So length times length per time, length cubed per time, times the density. And the density of a fluid is mass per unit volume, so that's mass per length cubed. So this is length times length per time times mass per length cubed. So this whole thing is mass per unit time. So this is describing the mass of whatever is the mass quantity in this density flowing through that face in a unit time. Likewise, if we come over here to the other side, we don't have this velocity because the speed might have changed. U might be a little bigger, a little smaller on this side. We're imagining that this cube is actually a rectangle, so the delta y and delta x, the sizes of this face, are supposed to be equal to the sizes of this face. But if we use a Taylor series expansion, we can express how rho u, that is the density might be different on this side, the velocity might be different on this side, so over here it might be a little different, d rho u dx times delta x. This is expressing a Taylor series, so a linear approximation to how much this flux of stuff goes through. But of course, since this has units of length and this has units of length, this whole object over here still has units of mass per unit time. So this is the mass per unit time flowing in on this side, this is the mass per unit time flowing out on this side. And the difference between the two, if there's no inflows or outflows on the other faces of the box, would give the rate of change in mass inside the box, which is, cancel this term with that term, just this. The gradient of rho u in x times delta y, delta z, that's the times the volume. So we see that the gradient of rho u, this quantity rho u, which is called the flux, is really important in terms of the rate of change of mass inside the box. A different way of thinking things is, what if we don't stay fixed in space, but we stay fixed in mass? We draw a weird, now it's going to be a weird kind of shaped object that contains a certain amount of fluid. If it contains a certain amount of fluid, then its mass does not change. We could imagine that there was a fluid loss through flows coming through the surface, or we could imagine this surface and the volume itself follow so that there's never any puncturing rho v, that there's no flux through the surfaces, in which case there wouldn't be a mass increase. Let's look a little bit at this calculus. This is rho v dot ds. So this is a dot, that's a normal flow of flux through the surface times the area of the surface. If you remember your fundamental theorems of calculus, this is backwards on the divergence rule. Here's the divergence of rho v everywhere inside the volume. So the divergence of rho v inside the volume integrated over the volume gives you this flux through the surface. And so the difference between this one and this one are, in the integral form, this surface, this volume are changing in time as this mass evolves. This one is not changing in time. Okay, so there is a concept that links the Eulerian and the Lagrangian perspectives. Something called the material derivative. It's the thing that lets you convert between a Lagrangian conservation law and an Eulerian field. Okay, so when we have something that tracks with a fluid, like salt, heat, momentum, we'd like to budget for it. However, we don't want to keep track of the individual parcels, because like we said, the slippery sacks are too many of them. But we can write the conservation law in terms of the material derivative, this thing, big d dt, which allows us to produce Eulerian equations. Everything on this side can be evaluated in Eulerian space. But this big d dt is the rate of change following the motion of the parcel, of every parcel. So this big d dt is the thing that is a Lagrangian quantity, but writing it out like this means partial of whatever that stuff is with respect to time, and its partial derivatives holding the fixed coordinates, holding x, y, z fixed. This is the velocity, so dv dx, this is the v in the x direction, the v in the y direction, the v in the z direction, dotted into the gradient operator. So v in the x direction dot d by dx, and it's partial d by partial x, the same thing. And again, we're saying partial, holding y and z and time fixed. So everything over here is Eulerian, staying fixed at a point in x, y, z. Everything, and this is a material derivative. So we're going to talk a little bit about more where this comes from. One way to think of it is it's just the chain rule. So we think about the rate of change in time of something like temperature, say, depends on time, x, y, and z. We could take the derivative on each of these independent coordinates on which the temperature depends. The temperature depends on time, but it also depends on x. So how do we do that? Well, we need to look at how the different arguments, the different independent coordinates that on which the temperature depends, vary with respect to time. So the first easy one is, how does t depend on time? Well, the total derivative as a part, it's just the partial derivative with respect to time. So t, take the derivative with respect to time inside, that's this first one. But now, since this is a total and not partial derivative, we also have to think whether x might depend on time. If it does, then we would take the derivative of x with respect to time times the derivative of t, the temperature, with respect to x. That's this term. Same with y, same with z. And so, now, looking at these, this is just the total derivative in general for any function of t, x, y, and z. What makes it a material derivative is we choose special dx, dt, dy, dt, dz, dt. So the partial of x with respect to t is not any old rate of change of x with respect to t. It's the rate of change of x with respect to t that the fluid itself does. So the fluid velocity is what talks about the rate of change in x with respect to time that the fluid is being displaced. So if we replace this with the fluid velocity in the x direction, we get a term that looks like this. Here's dt dx, and here's vx. Here's partial time, same thing with y, same thing with z. Okay, look at this. There's vx times the x derivative, partial derivative, vy times the y partial derivative, vz times the z partial derivative. Hey, look, that's partial temperature with respect to time plus v dot grad of temperature. And that's just the material derivative. So that's the same thing we started to talk about here, just written out as a chain rule over time, over a function of time and space, with the special exception, this is what makes it a material derivative and not a total derivative, that the way that this x depends on time is following the velocity of the fluid. Another example, maybe not rate of change of temperature with respect to time, but the rate of change of velocity. Now this is a vector quantity with respect to time, but we know what the rate of change, the total rate of change of fluid parcel with traveling with velocity v is changing. That's the acceleration. So this is the thing, this is the A in force equals mass times acceleration. It's going to be something like this. It's a ddt of v. Okay, by the same logic we just showed, you can take the total derivative, so first x on t, then x to the extent that x depends on t, y that depends on y, bing, again following the fluid motion. But now look, the argument here is a vector in each case, because v is also a vector and so is a. So we have an acceleration of v at the point, but we also have this funny other term, which is the v dot grad v dot grad v term. This thing is interesting. How does it work? The components of the velocity are hooked onto the components of the gradient. So those look like a scalar. There's no lingering components. But this velocity over here is still a vector, and so is this one. You can add them together because they're two vector quantities. So this beast gives you a vector answer, and that is the material derivative for v dt. So the total derivative of v under the special conditions that the partial derivative of x with respect to time is the motion of the fluid gives you the material derivative of v. So that's what it looks like in the differential equations. No integrals here. What about if we're thinking about the budget for that control volume? Now we might want to take the total derivative with respect to time of the volume integral of some property. Well, if that volume doesn't change in time, then the total derivative can just come right on the inside. It turns into a partial derivative, and bingo, we can write the total derivative with respect to time of an integral as the partial of that same property within that volume. And the reason why the t can move through the integral, this differentiation, is because the volume doesn't depend on time. And so we can think about the rate of change of mass in the control volume is the total derivative of the integral of volume dt rho dt, and so the integral of density is mass per unit volume, so the integral of volume of density is just the mass, so the rate of change of mass in the control volume is the volume integral of the density, which is equal to, by this idea up here, we bring the ddt inside, now it's the partial derivative of density integrated over the volume, which, how much does the mass change? Well, the mass changes if there's flow into or out of the box. That's what we talked about before. The flux, rho v, dotted into the area. So this is the normal velocity flowing through the sides of the box, integrated over all the surfaces. Or with the divergence theorem, we can write it this way, where it's the integral over a volume of the divergence of the flux. It's going to be equal to that mass change, or equal to the partial derivative of rho d volume. Okay, now look at these two right here in the middle. They're both integrals over volume. This is a derivative. This is a different derivative. There's a minus sign here. We never specified exactly what volume it was. So these two the equality between these two integrals can't depend on which volume we picked specifically. In fact, we could have, if there was a place where some small location where this integrand didn't equal this integrand, we could make that volume just single out that spot, and then it would be unequal. This equality would not hold. So what that means is that it's not just true for the integrals. Even though we argued this was the integral of stuff flowing in and out, this was the mass over the integrated region, it must actually be true that the integrands follow this relationship. And here it is. So this is the differential equation for the conservation of mass for a fluid of a given density. And it comes from this kind of argument in terms of control volumes, but actually we can write it as a differential equation because it didn't matter which control volume we chose. If we want to go the other way, we can also think about a control mass. What about the conservation of mass in a control mass case? Well, now we're talking about the material derivative, the total derivative of this volume, which is the material derivative of the mass and the control mass, which is 0. If we simply try to push this inside, we actually have to have two parts. One part of it is when the derivative acts on the integrand, that's this, and one part is when the derivative acts on the volume, because now the volume is changing in time. Without showing that math, you can trust me that there are two parts to that. The first part looks just like this came inside. The second part is this piece, which says that it's the density times the divergence of the velocity. So think about the divergence of the velocity as being if the control mass expands or contracts altogether, that's really the rate of change. That's the rate of change of the volume of this control mass. And so multiplying the density times that is like the part of this integral that changes because the volume is changing in time, not because the density is changing in time. So this is the one because the density is changing in time. This is because the volume is changing in time. You add those two together and you get the material derivative of the mass and the control mass, which is equal to 0. That's this side of the equation. That's this equation. Now, okay, stare at these for a second. Is this equal to this? In fact, they are, because if we went back to the definition of material derivative, this partial derivative plus v dot grad, and now we look at these. If this has the material derivative, this is the partial derivative of rho, that's the same as this term. And then the other one, v dot grad rho plus rho del dot v, put those two together, that's actually what happens if you take this divergence of rho v and distribute it out. You get one term where the divergence acts on v, which is multiplied by rho, that's just equal to this term, and then the other term is v dot gradient of rho, which is the other term sitting inside of the material derivative. So we didn't actually have to have a real bounding domain. We could have just had a numerical model grid cell to be acting as our control volume, or it could have been any weird thing we came up with. The only thing that we've used about the control volume approach is that the edges of the control volume are not changing in time. And it turns out that this kind of budget is how all the fundamental equations of motion of a fluid work. If we're conserving momentum or mass, we get an equation like this that has a material derivative for velocity or momentum, if you write it a slightly different way. There's one that's the conservation of mass, which is one of the two that we've already seen. One for the mass of salt or salinity. One for the energy. One for the entropy. There's another kind of equation that talks about the equation of state, which relates the density, the salinity, and the entropy. This is something we'll get to later. But all of these conservation principles are all written the same way. They're written as a control mass or control volume approach with a material derivative, in each case, of some property that's conserved. We're going to come back to these in much greater detail, just hinting at where this is going. This equation, however, is pretty complicated. This is if density is changing and velocity is changing, this is a nonlinear term. If there's not a nonlinear term hiding inside of here, and in any case, this is a partial differential equation, really complicated. We might have a much simpler story if we just set the density to a constant. Make the density of the fluid the same everywhere in space and time. Then this material derivative would be 0, and this part would just be multiplied by a constant, which we could divide through and cancel out. So that would just say that the divergence of the velocity was equal to 0. This is very close to what we do in oceanography, this incompressibility constraint. We normally make a slightly weaker version of this, which is called the Boussinesq approximation, where we allow the density to vary just a little bit, but not so much that this isn't approximately true. So think about if this is a small term, and this density is nearly constant, but for a little correction, then we could still say that the divergence of velocity was approximately equal to 0, but we wouldn't also say that the material derivative of the density was equal to 0. It would be slightly non-zero. Just this term is a lot smaller than this term would be. Does that make sense? In the ocean, the density varies from the most rarefied surface waters to the deepest abyssal ocean by about 3%. So thinking about a nearly constant density is actually a good approximation for us. So if it's approximately true that a fluid is incompressible, we can think about what might happen if we took a control volume that was rather interesting, like maybe an estuary, like Narragansett Bay with the Providence River and the Seekonk River flowing in, and then the exchanges here at the West Passage and East Passage, and Sakonnet rivers flowing out into the Rhode Island Sound. If we take all those inflows and outflows over here, they're not going to equal 0 if we add them all up, because we know there's river flow coming in. And we know that there's also precipitation on the surface bringing in fresh water and evaporation taking fresh water out. What this equation says is that ultimately all of those velocities have to balance out. Well, how do we get from this to this? Well, what if we integrate this divergence of velocity equals 0 over the volume of the bay? The integral of the divergence of velocity through the divergence theorem is just the surface integral of the velocity normal to the surfaces. That would also be equal to 0. So the surface integral, that is V out plus V in plus precipitation plus evaporation plus river inflow, that's what's equal to 0. Sum all those up through the surface, this surface, complicated surface with the bottom and the sea surface and the rivers and the over the sill, that surface is the surface that we would be thinking about for our control volume. So if we integrate over the estuary, just like I said, we integrate the divergence of V. That's equal to the closed integral of V dot ds. That's the divergence theorem, which then could be broken up into being the inflows through the different surfaces. The inflow surface, the inflow surface, the outflow surface, the surface for precipitation, the surface for evaporation, and the surface for the rivers. There's some interesting questions about the units here and whether this all works. Yeah, well, here's a volume flux. This is in units of meters cubed per second. So how much volume is coming in this flow per unit time, which is the velocity times the cross-sectional area. This is the outflowing volume flow. So again, this velocity times the cross-sectional area there. The area of the surface times the precipitation, meters per year, or whatever you like to think of precipitation in. Same thing with evaporation. And then the river runoff here is just taken to be a volume flow in this direction. So the speed, the velocity of the rivers times the cross-sectional area. So the inflow and outflow over here are balanced by evaporation, precipitation, and runoff. This is called the freshwater budget of a estuary. What about the salt? Could we also budget the salt? Well, yeah, sure we could. We could play exactly the same game, but with a conservation of salt, of salinity budget. And the interesting thing, the salinity is also a mass per unit volume or a parts per unit volume budget, which means that it's also a density of sorts. It's the mass of salt per volume or per mass of water kind of budget. This is what the salinity equation looks like. It looks a whole lot like the density in the mass conservation equation, except you could actually have a source of salinity, like maybe a chemical reaction, like suppose you're mixing sodium and chloride together and turning it into salt, or doing some other fancier chemistry and making an additional salt. But normally we think of that part of it as being 0. So it looks a whole lot like our conservation of density, but except now we're using salinity in place of density. If it's incompressible, then we can make the further step that we get an equation that looks like this, where now the difference between this and this is just the one of the two terms when we distribute this divergence out onto the v dot s. One of them is s del dot v, and one of them is V dot grad S, and the S del dot V1 goes away if it's incompressible, which means that this and this are equivalent equations in the case of incompressible. That's kind of a nice feature. And if it's incompressible, then we can, then that's all. Sorry, I wasn't even looking at this equation. This says what I just said in words. What if we integrate this equation over the control volume? Now we have a partial derivative with respect to of the salt with respect to volume, and then we have a divergence. So this divergence becomes a surface integral, wherever it is, becomes a surface integral. This rate of change, we can bring the rate of change outside. Why can we do that? Well, because this is a control volume, so none of the domain changes in time, just the integrand. So this comes out. It actually becomes a total derivative with respect to time. And now, what is this? This is the total derivative with respect to time of the salinity in the basin, which we could say might be close to zero. The salinity might be on average close to zero. If it is, then our bay would be pretty steady. You could also think of this, alright, this isn't quite correct to have our density in here. You could also have thought of this as being proportional to this, which is that the ddt of the density times the salinity. Density times salinity is going to be just the mass of salt inside the bay. This is saying that the mass of salts would be close to, the rate of change of the mass of salt would be close to zero. If we take these two pieces as ingredients, then actually what we find is something like this. The salinity times the velocity, the flux of salinity through the bounding surfaces is equal to zero. And now if we go back to what our different bounding fluxes, if the river water is fresh, it doesn't carry any salt. If evaporation doesn't take salt out, and precipitation doesn't bring salt in. So the only budgets we have to worry about with salt are the outflow and inflow here at the ocean side. And so they must be equal and opposite in direction, but with the way the arrows are drawn on, that means that the Vn times the salinity in is equal to the V out times the salinity out. It's actually not quite as simple that these are constants. It's really more of an integral, so it's really the average, if the velocity isn't constant over that inflowing surface or outflowing surface, you can think of it as a surface integral of the product. But if it was constant, the velocity was constant over all the inflow, and the salinity was constant over all the inflow, and same for the outflows, then it would be something simple like this. So can we apply this, and what could we learn? Here's a nice example of the Mediterranean as one big estuary, or the Black Sea as one smaller estuary. The Black Sea has a few rivers coming in on this side. The Mediterranean has both rivers and the Black Sea outflow, and of course is evaporation and precipitation. But now we're going to look at some real numbers. For the Mediterranean, there is actually an inflow near the surface of water that is fresher, 36.3 parts per thousand salt, and an outflow of deeper water that is saltier at 37.8 parts per thousand. All right? So we don't know what the rate of inflow is or the rate of outflow is at this moment. We just know what the different salinities are. What about the Black Sea? Well, the Black Sea has an outflow of surface water that's extremely fresh, 17 parts per thousand, and an inflow of 35 parts per thousand. Okay? So what does this mean if we go through our budgets? Well, we have two different budgets. We have a budget for the fresh water, which says that the outflow minus the inflow is equal to the runoff, the precipitation minus the evaporation. So these are the non-oceanic sources of fresh water, and this is the oceanic sources. Those two have to be equal to the freshwater source. And the salt source is just the ocean flows in and out times, which is these two, but with a salinity multiplier. We actually can combine these two equations to either eliminate the outflow from both, which is this equation, or eliminate the inflow from both, which is this equation. So stare at this for a second, see what you see. This side says that the inflow, the amount of water that comes from the ocean, is equal to a ratio of this funny thing, which is the outflowing salinity over the difference in salinity between the inflow and the outflow, times the freshwater source. So the inflow is proportional to the amount of fresh water, that is evaporation, precipitation, runoff, times some funny ratio of salts. If the inflow and the outflowing salinities are really close to each other, this ratio is really, really big, which means that the inflow is going to have to be a lot bigger than the freshwater source. That's interesting. That means that there's a large overturning in the bay for a certain amount of inflow and outflow if the salinities are close. If the salinities are far apart, then you don't have so much of that. If one of the salinities were fresh, then you would get to a limit where the fresh water, so suppose inflow was equal to fresh water, and that made it 0, then this would just say that the fresh water and the inflowing velocity would be equal to each other with an opposite sign. What about the outflow relationship? This is something similar, except instead of the outflowing salinity on the top, it has the inflowing salinity on the top. So you can go through this kind of logic to think this through. What does this tell us in the Mediterranean? Well, the Mediterranean is such that its evaporation is much, much bigger than its runoff and its precipitation. So we expect the water in the Med is going to get saltier. We plug in these ratios, bing, bing, we find, and we use some observations of the inflow rate and the outflow rate. Sorry, if we use the observations to infer the inflow rate, we can infer that the outflow rate is this. These two are quite close to each other with a relatively small, 2 orders of magnitude smaller freshwater source. So there is a net evaporation, but there's a really big overturning of flow in at the surface and flow out at depth, slightly saltier water at depth. So, and these two don't have very different salinities. So what does that mean? It means that the fact that these two salinities are close to each other means that there's probably a lot of mixing in the bay to take this inflowing water plus the evaporated water that is higher in salinity and mix it up to come into this saline outflowing water. And that's what we can tell from just this simple budget. 2 budgets, the budget of fresh water and the budget of salt water. By contrast, if we go to the Black Sea, it has a very big difference between the outflowing and the inflowing water. And so if the observations yield this, then Knudson's relation will tell us both the outflowing conditions and the freshwater source. So now look, these 3 are all close to the same magnitude. The outflow is really quite obviously just the sum of these 2 equal parts. So apparently the rivers in the Black Sea and the precipitation brings just about as much inflow as the inflowing water at depth does. These are pretty comparable to each other. The outflowing water is just the sum of those 2 basically. And look, that's because, we go back up here, that's because this inflowing and outflowing salinity are quite different, which makes these ratios numbers that are about 1/2. So that tells you that the freshwater and the inflow, this ratio is about 1 actually. So these 2 are close to each other. This ratio is about 1/2. So the outflowing is about twice as much as the freshwater. We didn't have to use salt. We could have used other conserved properties like pollutants. And so because of that factor with the mixing and the fact that the inflowing and outflowing salinities were so different in the Mediterranean, similar in the Mediterranean, different in the Black Sea, that tells you that the Black Sea probably hardly dilutes pollutants, just like it hardly dilutes the salt and the fresh water by mixing them up. And so the rivers of the Black Sea whatever pollutants they have pretty much go straight into the Mediterranean without dilution. Whereas the Med Sea, because of this rapid mixing, ends up quickly diluting the pollutants. So there won't be a big concentration difference in pollutants between the inflowing waters and the outflowing waters at the Straits of Gibraltar at the mouth of the Med. And so this is just another factor of doing this. So we haven't talked anything about what causes any of these flows. We haven't talked anything about the forces or any of that, and we've already gotten all of this just from thinking about budgets. And again, we could have used a control volume like this. We could have used a control volume that's shaped like a bay. We could have piled these boxes up side by side and thought of them as integral that make up a bay. All of those are valid ways to go. And a key piece of this story, which if you were shocked by these, are the fundamental calculus theorems. It's good to review these. If this wasn't on the tip of your tongue, there's the regular old one-dimensional fundamental theorem of calculus, where a definite integral of a derivative is equal to just the thing that is being differentiated evaluated the endpoints. There's the divergence theorem, which is the one we used over and over again. And then there's the Stokes-Kelvin theorem, which we're going to use a lot when we get to talking about vorticity, which tells you that the curl of a vector field is equal to the surface integral of that vector field. This is a little bit of a different game. This one's a little bit trickier to think about and visualize. All three of these, though, are useful quantities, and we're thinking about making budgets. That's it. Thanks.